In this video, we're going to talk about the fundamental theorem of calculus. The essential idea behind the fundamental theorem of calculus is that anti-differentiation, or a really definite integration, is the inverse of taking the derivative. Essentially, through this course, we've walked through the process of defining the fundamental theorem of calculus, where we took a look at a secant line and we knew that that was a slope, and we approximated the slope of a tangent line because secant lines and tangent lines are different. And also we've walked through, the area of a rectangle versus like the area under a curve is approximately that area. So historically, where that leads to in theorem speak is the fundamental theorem of calculus. So what that theorem states is that if a function f, so lowercase f, is continuous on the closed interval from some a to b value, and capital F is an antiderivative, then our definition of that integral from a to b of little f of x is equal to big F of that b minus big F of that a. So remember, the little f right here is your derivative, and the big F is the antiderivative or the original function that produced the derivative. And so taking that a step further, there are some practical guidelines for using this theorem, and that first, if you can find the antiderivative, you now have a way to evaluate a definite integral without having to use a limit of a sum. So I promised you a way to do that without a limit definition and without a sigma, and this is exactly what we're going to be doing in this video. So the second guideline is when you apply that theorem, the notation is shown like this. So it goes from this like funky S thing, the integrand, to looking like a bracket like that. So those A values still line up and those B values still line up, and it's still that definition of the antiderivative of B minus the antiderivative of A. So for example, let's say that I wanted to find the integral of x cubed from 1 to 3. So that's the area under that curve from x equals 1 to x equals 3. So this is the notation that we would write. So x to the 4th over 4. Remember our antiderivative rules, that's a power rule for integrals. And so all I do is plug in 3 here, and so that becomes 3 to the 4th over 4 minus, and I would plug in 1 to the 4th over 4, and that actually gives me the area under that curve. And so just a third guideline that you may be thinking about is that when you take the antiderivative, don't we always have a plus c? And yes, that is true, especially with indefinite integrals where we don't actually know what our a and b values are. But if you do take into account that you have some c value, it's going to be the same c value. So plus c minus c goes away. So that's why we just have big F of b and big F of a. All right, and now for my favorite part of a video, which is working through examples, and I'm sure you love it too. So let's take the integral of this function here, so x squared minus 3 from 1 to 2. So the first step that I have here is I'm going to take the integral of x squared minus 3, so that becomes x cubed over 3 minus 3x over 1, which I don't include. And then here's my new notation, this big old bracket with a 2 and a 1, which are the same as over here. So I'm going to plug these two guys in and see what happens. So what I end up doing here is I take the b value, which is the top value up here, so 2, and I plug it into this function. So I get 2 to the 3rd over 3 minus 3 times 2. And then I do the same thing with 1. So I subtract that 1 to the 3rd over 3 minus 3 times 1. And then I work it out with some arithmetic, and I get negative 2/3 is the answer to that integral. All right, so let's work through something that may not be as clear cut. I don't know how you feel about the square root function. So I'm going to actually rewrite this integral. So what a constant multiple allows me to do here is to pull that on the outside. So I'm going to have 3 times this integral. So from 1 to 4 of x to the 1/2 dx. And so what I have here is the integral of x to the 1/2. So it's x to the 3/2 over 3/2, all times 3 right here. And those 3's actually end up canceling out. We have the 2 x to the 3/2 from 1 to 4. So I'm going to do like I did up here, plug in my 4 and my 1. See what I got. So I plug my 4 in for the function here, and I plug my 1 in here, and I get 2 times 8 minus 2 times 1, which gives me 14. So the area underneath this curve from x equals 1 to x equals 4 is 14. So let's work through another example, and let's say I have the integral of this absolute value of 2x minus 1 from x equals 0 to x equals 2. Something that we need to take into consideration is that the absolute value function is actually a piecewise function. So I have to consider two parts of this function. So it is a line with a negation of 2x minus 1 here, negative 2x plus 1 if you'd rather, and also this 2x minus 1 wherever. So this comes into where x is 1/2, and that goes to the positive 2x minus 1 when it goes to the right of 1/2. So algebraically, how I deal with this is I take the integral from 0 to 1/2 of the negative part of the piecewise, so that negative line, and I add it to the integral from 1/2 to 3 of the positive line, so 2x minus 1. So what I do is I distribute the negative to make that negative 2x plus 1, and I take the integral, so it becomes negative x squared plus x, so that's from 0 to 1/2, and then the integral from of 2x minus 1 is going to be x squared minus x from 1/2 to 3. So I'm going to plug in my values and figure out what the area is right here. So I evaluate for 1/2 into this function, which gives me negative 1/4 plus 1/2, and I evaluate 0 into this function, which gives me minus 0 plus 0. And then over here, and in this bracket, I'm going to have the evaluation of 3, so x squared minus x for 3 is 4 minus 2, and then I'm going to subtract 1/2 into that expression, so that's 1/4 minus 1/2, put that all together, and the area underneath this is 5/2. Could you have also split this up into geometric figures and figured it out that way? Of course, but this is just another way using the fundamental theorem of calculus for us to do that. So here's an example where we have to actually set up the integral. So let's say I have this quadratic, so 2x squared minus 3x plus 2, and I want to know the area under the curve that's bounded by the x-axis and x equals 0 and x equals 2. So knowing my bounds from 0 to 2, that's my a and my b, and my function is whatever y equals, and then I tack on a dx because we're doing this in terms of x, so let's write this out. So this is going to be the integral for our function here from 0 to 2. So let's plug in those values and see what the area is. And so when I plug in 2, this is the quantity that I get. When I plug in 0, of course, I'm going to zero that whole thing out. So this quantity is equal to 10/3, which is the same as the area underneath that curve. So I've got two more theorems for you in this video. So we've talked about a mean value theorem for derivatives, and there's one for integrals as well. So in theorem speak, that is f is a continuous function. It's on a closed interval from a to b. Sounds familiar? Then there exists a number c in the closed interval such that if I take the integral of f of x, it gives me the function of some c times b minus a. So what this theorem is actually saying is that somewhere between the inscribed and the circumscribed rectangle, there is some area c of that rectangle here in the middle that is actually equal to the actual integral here. So this doesn't tell you what that c value is, it just says that, hey, it exists and you can find it. And our last theorem here in this video is the average value of a function on an interval theorem or definition. So that f of c value that was given to us in the mean value theorem a slide ago is called the average value of f on that interval from a to b. So how you find an average value is you take the integral that we've been working with, so from a to b of f of x dx, and you multiply that by 1 over b minus a, and that gives you about the average value of what that thing would be. So let's try on an example of that for size. Let's find the average value of this function, so 3x squared minus 2x, which is a nice quadratic, on the interval from x equals 1 to x equals 4. That is bounded by the x-axis. So we know that this is the average value equation, so I'm going to plug in my b and a and my f of x, and from here I'm just going to carry this 1/3 all the way down and multiply that definite integral. So the integral here is 3x cubed over 3, which becomes x cubed, minus 2x squared over 2, which is just minus x squared. I plug in 4 and 1, and I get 48 over 3, which is 16. So the area under this, the average value there is going to be 16. All right, that's going to do it for this video. Thanks for watching.